Welcome to my talk on uncovering some of the fastest terrestrial networks and what we can learn from them. I will talk about high frequency trading or HFT networks in the Chicago New Jersey corridor. Uncovering and analyzing these ultra low latency networks allows us to learn about some of their interesting design choices. On the Chicago end, we have the Chicago Mercantile Exchange or CME data center located in Aurora, Illinois. If we zoom in, we could see the data center located pretty close to Lake Michigan. On the other end, the Equinix NY4 data center, the New York Stock Exchange or NYSE data center, and the NASDAQ data center. The geodesic distance between CME and these three data centers is roughly 1180 kilometers. Within this corridor, changing market conditions at one end triggers algorithmic trading at the other end. So every microsecond gives an edge to the HFT participants. The fastest HFT networks eschew fiber in favor of line-of-sight radio connectivity. An end-to-end connection between two financial centers comprises a series of point-to-point connections between radios mounted on tall towers. Each tower functions as a simple repeater. This strategy allows financial centers to connect along nearly the shortest possible paths on the Earth's surface at the speed of light or c speed. The last mile between the data center and the first hub is speculated to be optimally laid fiber. Various web resources discuss interesting anecdotes and insights into HFT networks. None of these, however, present a systematic way to collect and analyze information on these networks, but instead rely on sources of information as esoteric as details of court cases on real estate close to the data centers. Our work, in contrast, conducts a systematic analysis based on publicly available FCC filings data. We analyze several present-day HFT networks and show how they differ in their network design strategies. From this comparison, we draw takeaways for building future low-latency terrestrial networks. Each microwave link is represented by an approved license in the FCC database. Each license file contains information about tower locations, link properties, licensee, and important dates governing the license. More precisely, from each filing, we can know about the grant, cancellation, and termination dates of the license. These dates allow us to check if a license was active at any date in the past, location and height of the individual towers, and implicitly the line of sight link length, and operating frequencies of the link. Our tool scrapes the FCC database to gather useful information for reconstructing the HFT networks. We use the geographic license search to find all licenses within a radius of 10 kilometers from the CME data center. Next, we use the site-based search to select only those licenses that have a radio service code MG or microwave industrial or business pool and an assigned station class FXO or operational fixed. Our tool can reconstruct a network at any arbitrary date in the past using its licensing information. We assume that if a license is active, that is, it was granted but not terminated or cancelled, its microwave links are active. We reconstruct entire networks by stitching together their individual links. A tower that is an endpoint for two links forms a node connecting these links. Assuming data centers have fiber connectivity to nearby towers, one can estimate one-way end-to-end latencies between data centers based on the path lengths divided by the speed of light. If we look at an individual microwave link, it contributes to the link latency, which is link length divided by the speed of light or c speed, and the switching latency incurred at the tower hubs. Note that we do not account for the switching latency while calculating path latency. Path latency is rather the sum of fiber latency incurred at each end and all the link latencies along the end-to-end path. This figure shows the latency evolution since 2013 of some of the fastest networks for the CME NY4 path. The smallest end-to-end latency on this path has decreased from 4 milliseconds in 2013 to 3.962 milliseconds in 2020. National Tower Company's network ceased to exist in 2018, while Pierce Broadband, the second fastest now, came into existence only in 2020, thus showing how this ecosystem is continuously evolving. Note that the latencies here are path latencies at c speed, without taking into consideration switching latencies at individual hops as we discussed before. These are the 9 connected networks between CME and Equinix NY4 as of 1st April 2020. New Line Networks has the shortest path network between CME and NY4 as of this date. And the difference in path latency is 0.4 microseconds with its immediate competitor Pierce Broadband and 4.3 microseconds with Jefferson microwave. Note that Jefferson microwave has 3 less hops along its shortest path. If both NLN and JM were using the same radios and the per hour added latency was higher than 1.4 microseconds, JM would offer lower end-to-end latency. I'll come back to this table and discuss APA few slides later. Our tool can also capture the evolution of infrastructure over time. Note that PS Broadband had no infrastructure back in 2016. By 2018, they laid many microwave links in the corridor, but the network was still disconnected. In 2020, they have an end-to-end connected network and offers the second best path latency between CME and NY4. Note how the other networks also evolved during this period. New line networks, for example, has added many new links. If we compare their network in 2016 to the network they have now, we'll see how the additional infrastructure has moved closer to the geodesic over time. Let us now compare some network properties of new line networks or NLN and web line holdings or WH. In this fierce competition where each microsecond matters and slower networks like National Tower Company perish over time, how do networks like WH manage to survive? A definitive answer to this is likely not possible without closely guarded industry insider information. But the rich information available from the filings allows us to speculate on a likely hypothesis. For each network, we find the fraction of links that can be removed such that the latency of the remaining network is not more than 5% greater than the C-speed latency along the geodesic. This fraction is referred to as the alternate path availability or APA. Between CME and NY4, WH has an APA which is significantly higher than that of NLN. This is true for all the paths in this corridor. Higher APA translates to more alternate paths in case certain links become unavailable due to bad weather conditions, interference, or other unforeseen events. For both networks, we compute all loop-free paths between CME and NY4 that achieve latency within 5% of the C-speed latency along the geodesic. This figure plots the CDF of tower-to-tower link lengths for all microwave links on such paths. The median length for WH is 36 kilometers, which is 26% lower than NLN, which has a median length of 48.5 kilometers. WH is thus exposed to lower path loss and is more robust to attenuation. This figure shows the frequencies used between CME and NY4 for microwave links on the shortest path for each network. WH primarily uses the 6 GHz frequency band, while NLN uses the 11 GHz band. What is interesting is that the green dashed line, which also takes into account alternate paths in the NLN network, shows that 18% of the frequencies lie in the 6 GHz frequency band. It is well known that lower operating frequency translates to lower path loss and less attenuation due to rainfall. Thus, along each of the three metrics tied to reliability, WH scores higher than NLN, even though WH's latency is higher than NLN's by a few microseconds on the shortest path. Thus, in challenging conditions, WH could offer lower latencies than NLN. The most competitive trading firms may even use a combination of both services to maintain their advantage in varied conditions. While the sub-microsecond competition of HFTs is immaterial to efforts like low-latency terrestrial microwave networks, such networks should be engineered towards high APA using redundant microwave links close to the shortest paths. Link lengths exhibit a complex trade-off. Longer links allow cheaper builds using fewer towers, but are also less reliable. Lower operating frequencies reduce weather disruptions. If the shortest path needs to operate at higher frequencies to cater to the bandwidth demands, alternate paths may use lower frequencies. All right, let us now briefly touch upon some future work. It would be interesting to identify the entities behind the licensee entities by analyzing items like the licensee email addresses and other publicly available information. For example, two licensee entities in this table have the same license email address and hence can very well be co-owned and operated by one entity. It is thus interesting to perform a joint analysis of their own infrastructure. In this specific case, we have seen that PS Broadband and Jefferson Microwave combined offers path latency lower than new line networks at the moment. Terrestrial microwave and millimeter wave networks can offer low latency over connected land masses, while satellite networks can breach the continental divide and offer long distance low latency connectivity. It would be interesting to explore design choices for hybrid terrestrial microwave and satellite networks for offering low latency connectivity in the future. Our code and data are already publicly available. We hope this work would be of interest not only for the network research community, but also for the finance community. With that, I thank you for your attention.